So I'm pleased to present Anubhab Roy, who's an associate professor in the Department of Applied Mechanics at the Indian Institute of Technology, Madras in Chennai, India. In 2013, he received his PhD in engineering mechanics from Jawaharlal Nehru Center for Advanced Scientific Research. I think it's easier to say the acronym, JASR. In biochemical engineering at Cornell, before joining the fluid mechanics group at Applied Mechanics at IIT in Madras. His work focuses on hydrodynamic instabilities and particle-laden flows with applications to atmospheric and oceanic flows.
Thank you. Thank you everyone for joining in. Today I'll be talking about problems on particle flow interactions with applications for cloud microphysics. So before I get started, I'll just acknowledge the people who were involved at different stages on this work. So a large part of what I'll speak in the second half of the talk is done by my former PhD student, Piyush. And some of these work got started when I was finishing my postdoc at Cornell with Don Cook, and the experiments that I'll be discussing were done by Greg Worth at Wesleyan, and Johnson was also involved in this, in some aspects of this work. So when we typically talk about scales of atmospheric motion, a small scale can typically mean sometimes even a kilometer if you're thinking of a global circulation model kind of resolution. But if you were to span out all the possible scales that are there, you can run into massive orders of magnitude difference between the largest planetary scales that you are interested in and the smallest possible scales at the aerosol level that are influencing the dynamics. And a focus of this talk today would be primarily going towards the bottom extreme and seeing if there is something new to learn there and how some of these can actually be viewed as problems of particles and flows that are there. So this is broadly the aspect of cloud and precipitation microphysics. And the way I'll be talking about this is in the context of a fluid dynamics problem. So my focus is primarily three aspects of this problem of cloud microphysics. Can we understand the microphysics of hydrometeors better? And mostly the objective is whether it's in the context of icy clouds, where we have ice crystals of a variety of shapes, their orientation dynamics, or it could be in the context of warm clouds, where we are thinking in terms of collisions and growth of droplets to larger size before they precipitate. So the part regarding warm clouds would be what I'll discuss in the second half. For now, it's the part of a single hydrometeor, which is an ice crystal. And the objective is to see that can we understand the orientation dynamics a little better than how we know typically for these problems. So they come, I mean, if one were to just look at the shapes and the sizes that are there for these ice crystals, the anisotropy that is inherent in this problem is something that comes up immediately. And the length scale that we are thinking of, so the bottom image actually gives us some sense of how big these crystals can be. They're typically of sizes that run into few hundreds of microns or sometimes could be smaller. So the driving goal that we'll have when we talk about such small particles that are present, that at the scale of the particle, the motion can be quite different than what we are used to thinking of, the large scale flows that are there in the context of clouds. So why is it important to study these orientation dynamics, especially in the context of these ice crystals that are there in cirrus clouds? So when one thinks in terms of doing a discrimination of what kind of hydrometeors do you have in these clouds, it often gets hard to distinguish between droplets that are there in clouds compared to the ice crystals if those ice crystals were not randomly oriented. So if you try to calculate the backscatter and find out what is your depolarization ratio, the depolarization ratio will be almost zero for spherical, basically water droplets. And if these were randomly oriented ice crystals, it would be non-zero. But when you have horizontally oriented ice crystals, it gets hard for it to distinguish between what is a water droplet and what are clouds which have these horizontally oriented ice crystals. So the point is, if you are trying to calculate these backscattering coefficients, the backscattering coefficient typically would require you to do
a calculation for a single crystal in some arbitrary orientation with respect to a tilt angle for the lidar that is sending in these light waves. So that gives you your backscattering area, which is this CBK. And you assume a certain distribution of these size of these crystals, and that gives you your backscattering coefficient. But in the process of doing this calculation, something that is key is what would be the orientation of these crystals. So if you assume that these are plate-like objects or these are column-like objects, one key parameter is their tilt with respect to the vertical direction. So that's the angle capital theta that is given here. And you could either assume that it's all randomly oriented, so there is no particular bias towards any angle, or you can assume a certain form of distribution. So I'm just showing a distribution that is often assumed. You assume a Gaussian distribution. And this distribution comes about with a certain fitting parameter, a certain variance that is there. So that theta effective that you see. Now, does it matter? So if you were to use different value for this distribution in terms of how broad or how narrow this distribution is, you get quite different values of the backscattering coefficient. So on the left side, you see the backscattering coefficient plotted as a function of effective radius. So the different lines are for different values of that tilt. So if you assume that the distribution basically has a variance of around 0.5 degree or 1 degree up to 5 degrees, you see that the sensitivity to the backscattering coefficient can be quite high. And this is for a lidar which has a tilt angle of 3 degree. So this is just to emphasize the point that it's probably more important to understand how these orientation distributions should actually be. And the part regarding flow is not there. So effectively, the orientation distribution should be determined by the background turbulence intensity, which is nowhere there in the distribution itself. So we'll try to see if there is a way to first understand what should the on an average orientation be, and if it's possible to arrive at some sensible orientation distribution for these ice crystals. So the attempt to understand these orientation dynamics of ice crystals is fairly old. And these were started off in classical tank experiments. So this is the paper by Javira and Mason, where the idea was to understand the process of rimming, that when you have an ice crystal that's falling and it collides with a water droplet, they start to basically form these bulbous ends. And the point was to see that what would be the orientation of these rimming or these rods which start to develop bulged up end in one side. So what they did in the experiment in the lab was they considered a single rod, which was an isometric rod, and they fused a sphere at one end of the rod. So that gave you two parameters to play with. One is the offset of the sphere with respect to the center of the rod. That's your asymmetry in terms of the geometry. And you can also play with another parameter, which is how heavy is the sphere that you are fusing with respect to the weight of the cylinder that you had. So if the sphere was exactly at the midpoint, then it doesn't create any mass asymmetry in the problem, in which case the rod would primarily remain horizontal. And that's what you actually see in the bottom in this axis, where the vertical axis is the weight of the sphere by the weight of the cylinder, and the horizontal axis is the asymmetry. So when the asymmetry is very small, there is a bias of more horizontally oriented rods. Whereas when the asymmetry becomes higher, you start to see more vertically oriented rods. And then somewhere in between, the experiments also observe that you have oblique orientation. So this is just a problem of pure settling. There is no background flow involved in this. You are just dropping rods with this kind of an asymmetry. And if you now ask the question that can we quantify this and study this better? Can we actually do calculations which are going to make predictions that can be matched with these experiments? So the point is, when I have any anisotropic particle, and as I highlighted in the beginning, these are reasonably small. So when I say reasonably small, my assumption is that they are primarily being driven by a very viscous flow in the surrounding, in which case the torque that is going to act in such an anisotropic particle, you can use symmetry arguments and say that the torque would depend on the two vectors that are in the problem, the settling direction and the orientation, the symmetry axis of the object. And there can be other dependence dimensionally based on density of the fluid, a characteristic length scale, and then a non-dimensional quantity that captures the aspect ratio or some kind of other aspect of the problem. So with that, if you go ahead, you can pose this question that if I have a symmetric column that was falling, the column would want to maintain a horizontal orientation. If I had a column which was bottom heavy, in absence of any hydrodynamics in the problem, it would like to lower its center of gravity and hence fall vertically. Now, when there's a combination of the two, you would expect that there should be some kind of an oblique orientation. And that's exactly what we carried out. So these were experiments done with asymmetric cylinders dropped in a fluid. The asymmetry was created instead of a geometric asymmetry. This was created as a mass asymmetry. So the cylinders were made and an air pocket was created in the cylinder in one end, which basically shifts the center of mass. And when you release them, the parameters which are explored here non-dimensionally, one is a non-dimensional measure of the settling speed, the Archimedes number, and the x-axis is the degree of asymmetry. So when you have very weak asymmetry, then there is a chance that the object is basically going to be primarily horizontal. And as you keep increasing the asymmetry, at some point there is a bifurcation, and beyond the bifurcation, it will always remain a vertically oriented rod. So we were able to see this, that using this first level theoretical approach of how we understand this as a competition of the hydrodynamic torque that is coming about due to the flow or due to the fluid that is there, and the torque, gravitational torque that comes from the asymmetry, you can nicely capture that what kind of a bifurcation that you will get as you go from rods that will fall horizontally or rods that will have more oblique orientation. And a point to note here that the orientation matters for objects that are anisotropic, because if they are oblique, they can also have lateral motion. It's necessarily not just going to go down vertically. There is a lateral migration that can also happen. But this is all in a quiescent background. There is absolutely nothing happening in the flow, in the background fluid, other than the disturbance that this settling object creates. So the question would be that what about the background atmospheric turbulence? So again, going back to, I mentioned about the tank experiments of Jayaveera and Mason, but there are also very nice experiments. I call them the cloud experiment, because this was done in an observatory which was at around 3,300 meters in Wyoming. So effectively, it was above the cloud base. And they were making observations of falling ice crystals, various kinds of studies regarding their fall speeds, but also trying to quantify the distribution of the oriented ice crystals. Percentage of how many of these were horizontally oriented and how many of these were more vertically oriented. So that's the study of Zikmund and Wali. So we again ask that if there is a background turbulence in the problem, whatever I have said earlier, even if I simplify it further to saying that let's forget about asymmetry, let's just think of just a single columnar crystal or a plate. Is there a way by which we can now say that how do we make measurements or in experiments, and how those measurements on the experiments can be compared with the theoretical predictions that we make? So we expect that in absence of turbulence that they should primarily be horizontal. That's the understanding. If it is a perfectly symmetric object, a plate would have its broadside settling, and a rod also would have a broadside settling. Now, if there was only turbulence and there was no settling, turbulence would like to randomize this orientation. So now we are looking at a competition between these two that are going to occur. So these are experiments again done in the lab. These are again tank experiments, more recent tank experiments done in Greg Watt's lab in Wesleyan. If you keep the dynamic similarity intact, even though these are done in a water tank with a turbulent background, they can be mapped to what happens in the atmospheric setting. So these are experimental data for the orientation distribution as a function of the inclination from the vertical. And you see that there is a peak that occurs towards the crystals or the rods basically being more broadside oriented. But the interesting aspect is as you keep increasing the turbulence, the PDF basically gets broader. So this is what I had in mind when I said earlier that when you are thinking of the calculation of this depolarization ratio or backscattering, there needs to be some way to introduce the aspect of background turbulence in this calculation. So we go back to saying that, is there a way where I said that they would want to be in a horizontal plane, but we would do a dance about it because of turbulence. So as if I introduce a non-dimensional measure, that how fast would it fall with respect to the background turbulence velocity scale. If the settling speed is significantly higher than the turbulence velocity scale, it would not really want to do a lot of wiggle about the horizontal plane. Whereas these wiggles would get more pronounced as the turbulence velocity becomes stronger with respect to the settling speed. So this is a regime where turbulence dominates over the background, over the settling, whereas this is a settling dominated regime. So here you are looking at an orientational variance, a measure of how much does it wiggle about the horizontal plane. So you have an isotropic configuration where it is 1/3 when it's only turbulence, and gradually it starts to decrease. And as it starts to decrease, it implies that it prefers to be in the horizontal configuration. And this has a dependence on the settling speed that decays with the 4th power of the settling speed. Now, this is in contrast to the existing theory, which says that any such anisotropic particle would have a decrease of this variance that would go quadratically with it. So the question is, why is this discrepancy, and can we actually quantify this? So the model that I introduced earlier of trying to understand the orientation dynamics that continues in the same spirit here, there is a torque which is there due to the settling motion. There is a torque that is there because it is rotating with respect to the background. And there is a torque that is there to the turbulence. And this is an overdamped dynamic. So you say that there is no angular acceleration for the crystal. So if you say that this is an overdamped dynamics, then all these 3 torques should be instantaneously in balance. If these are instantaneously in balance, you will be able to write down a description, an evolution for the orientation of these anisotropic particle that is dictated by a competition between the settling, W basically being the settling speed. The other parameters here, kappa is the aspect ratio of the rod, Reynolds number based on the size of the rod. But the important thing to notice here, you have the settling which is competing with the background turbulence. So now we go back to the same argument that if they were to settle faster than the time it takes for a turbulent eddy to complete one rotation, that's the regime where tau eta, the turbulent time scale, by the sedimentation time scale is significantly higher. So you can obviously solve this above equation numerically by having the information regarding the turbulent velocity gradients. But is it possible to get a measure of that decay that I mentioned, the discrepancy, that it decays differently than what is known in previous literature? So if we now say that it wants to be in the horizontal plane and it does this wiggle, so in the horizontal plane, there is a dynamics that is given completely by the background turbulence. There is nothing to compete there. But in the plane, in the direction perpendicular to the horizontal plane, you will have now a balance between the torque due to settling and the turbulent torque, which finally gives us this small fluctuation that you experience that depends on the velocity gradient, the turbulent velocity gradient. So running this through, you finally have now a measure that the variance, this parameter SF, I would like to remind you, scales quadratically with the settling speed. So which means that now I have the variance is scaling with the 4th power of the settling speed, as was seen in the experiments. And you can now run this with for the full equation. So you can either take the velocity gradient from a DNS data of the turbulence, homogeneous isotropic turbulence. Or if you want, you can also use various synthetic models of velocity gradient. So here I've given one model for your reference. This is a model for velocity gradient, where the velocity gradient is modeled as a stochastic process such that it replicates a log normal distribution for the pseudo-dissipation. So the advantage of using these models is that you can run it for much larger Taylor-Reynolds number. And the predictions that you get from the simulations are given by the blue squares. And the prediction that you have from the theory are given by the dashed lines and the continuous line. The difference between the two basically comes in terms of what we assume regarding the correlation of orientation and the velocity gradient. So what about the comparison with experiments? So we wanted to take this forward not just for rods, but something slightly more complex than a rod. So we took it for these kind of branch particles. So here the branch particles are 3D printed, and you see a whole array of shapes that are there. The triad or the Y shape is what I will focus on here. So you drop these particles and you track what their orientation is. So this is what the theory and the simulations predict, that now the Y-shaped particle would again want to be in the horizontal plane and execute a small wiggle about it. And when you compare them with with the results that you have from the experiments, it's a pretty good match that you get. So even with the simple theory that we are using here, we are saying that at every instant, you have the balance between the torque that is due to the hydrodynamics, basically being balance that is coming from the settling aspect. That gives us a way to quantify what this variance should be. And it measures well with what you actually get from the experiments. Now, the motivation was about this orientation PDF. So can we take this forward and actually make comparisons with the PDF? So I showed you the PDFs that we had from the experiments, and with the same theory, you can now also try to predict what the PDFs would be for such falling anisotropic particles in a turbulent flow. And some of the key things that come about, besides a nice match that you get, that there is a strong degree of non-Gaussianity that is there in these PDFs. And which is not very surprising because the inherent velocity gradients are non-Gaussian in nature. So when we are calculating these various moments, which are the orientation distributions, they are also replicating. So when you start calculating the higher moments, it starts to show up. The experiments also indicate the non-Gaussianity, and the theory also manages to capture that. So this is basically the part where we looked at the orientation of anisotropic particles. And here, just at the individual level of the particle, there is probably a lot that we can still do. For instance, as I said, like we have only focused on these being over-damped dynamics. If these ice crystals were to be much larger in size, you can take them forward and basically account for the fact that they can have their own acceleration. But it's still quite complicated to take this and study collision. So for collisions, for objects which are anisotropic, that's extremely hard. And as we realize that it's already quite challenging when we are thinking of the simpler entity, which are just water drops. And that's what I will talk about in the second part. So in the second part, I'm just focusing on the collisional dynamics of cloud droplets. So this is in the context of warm clouds. And the motivation is fairly straightforward here. We are thinking of the gap, intermediate gap, where a condensation-driven argument for growth is not sufficient because that would be extremely slow process. And a gravity-driven argument yet doesn't kick in. So there is something that is actually happening in between, which leads to the growth of these droplets. And the key question is, it's not what is driving these collisions. We know that the background turbulence is driving the collision. It's more to the fact that can we compute these rate of collisions in a more precise manner than how it's typically done? So if you start listing out that what would be the physics that influence collisions, and when I say collision, this is actually like particle-particle contact that's happening, you will start filling up the list of things that can drive collision. So I'll run through what is already there. So you can have the aspects of charges playing a role, the fact that they have their own inertia that can drive collision. There can be colloidal forces like van der Waals can drive collisions. You can have the thermal fluctuations for very small aerosol particles can drive collision. I've already mentioned turbulence. There is obviously gravity. There is the aspect of interfacial mobility, which means that these are drops. These are not solid particles. So there is an internal flow that is there inside. So this is not exhaustive. You can have fairly other physics that are all competing to undergo collision. But finally, what you are after is a rate of collision that depends crucially only on 4 parameters: the two droplet sizes, the dissipation rate, and the Taylor-Reynolds number. That's all that is there. So a lookup table which can basically give you the value given these 4 parameters is something that would be very useful to do evolution of droplet sizes. Any DSD prediction would essentially need this. So now, this is again not something that is recent. It's been there as a theory of coagulation that was put forward by Smoluchowski more than 100 years back. And the idea was just that if you have two particles which are moving around in a background flow or due to gravity, they just move oblivious to each other. And the moment they come in the neighborhood of each other, that is what you define as collision. So it's one way to say these are ghost collisions that are occurring. Because until you make contact, there is no signature of the presence of the other particle. So in Smoluchowski's original paper, there are two calculations that were done. One was for differential sedimentation, which means there is a bigger sphere which is lagging a small sphere. So eventually it catches up because it settles faster. And then once it makes contact, you call that as collision. So effectively what it tantamounts to is just finding that column that is the cylindrical column that is actually there for the excluded volume to define that what is the flux of particle that is passing through. The other calculation that was done was for a simple shear flow. So there is a linear flow which is increasing in the direction, in the y direction, and in the x direction is the flow. So again, you can define an intercept area here doing the calculation and finding the collision rate. Once the collision rate calculation is done, you can take this forward and basically argue for like a kinetic approach of how the sizes increase. Now, these were videos, these three. They won't play because it's a PDF, but I'll describe to an extent what's happening here. That when you do an actual scenario of two spheres that are moving around, so this is the scenario of two spheres which are in a background shear flow. They are obviously going to feel the presence of each other once they get close. So they can't just move in a straight path and pierce through each other. So once they get close, they are going to basically undergo a deviation, because as they're getting closer, there is a resistance that they experience because the fluid that is there in between the gap, that is getting squeezed. And because of that squeeze, they will experience a force that will deflect them. So there are different kinds of deflections that you can get, and that nature of deflection depends on what flow you choose. So this is what will always happen, whether you have a background shear flow or you have gravity. Irrespective of that, this is the problem of interacting particles. The particles are going to interact, and that interaction is going to influence what you actually call as collisions. So you can do these calculations of what I call as the real collision rate with aerodynamic interactions. You can do it for different kinds of flow problems, and it's again not something that's new. It's pretty common in the community of people who work in colloids, because that's where this calculation of coagulation rate is actually quite common. So what is that is different when we are thinking of cloud droplets? So in the scenario of colloids, it's understood that when these two spheres get close, as I said, they're trying to squeeze the fluid that is in the gap. And as it tries to squeeze the fluid, it basically experiences a resistance, which is the lubrication force, that scales inversely with the gap, which implies that if I were to fix the force and calculate the relative velocity, I'm basically never going to have contact in finite time. I need to wait for infinitely long time before any contact can happen. But this is never a botheration in colloids, because you say that as it gets close enough, there can be an inevitable physics of van der Waals force, such that once it gets close enough, that attractive nature of van der Waals will make them come in contact. Now, you can use that argument in the case of droplets in air and basically start asking that when does this lubrication approximation break down? And there are at least 4 of these reasons by which you can have this breakdown. So what I'm showing here in a plot where the y-axis is the gap between the two spheres and the x-axis is the size, an average size in microns. As the gap gets, as the particle size gets smaller, so you're moving towards the left corner, for smaller particles, van der Waals is basically what is dominant. So the way this is argued for, you say there is an attractive van der Waals interaction, and there is a lubrication force which is trying to prevent them from coming in contact. And balancing the two, you see that any particle which is actually going to be below this first dashed blue line is going to collide due to van der Waals interaction. And then if you start having much larger drops, effectively, once the lubrication force becomes very high, the drops can no longer be spherical and they're going to deform. And the deformation can also be responsible for the collision that might occur. And there can be also the aspect that the lubrication pressure can become comparable to vapor pressure, which can also induce collision. But effectively, if you just look at the top, as long as you are in a below 20 micron, van der Waals seems to be the winner. And beyond 20, 30 microns, the deformation should be the winner. This is what would be the picture until you account for the fact that everything here is happening in air, which means that around 100 nanometers, you have basically breached the continuum assumption. So the mean free path would be around 70 to 100 nanometers. So once that gap is breached, you can no longer do any of these continuum calculations, and you need to account for the fact that as they are trying to squeeze the fluid between, it's more of a molecular flow rather than a continuum fluid flow that you're having. And this is only happening because we're thinking of drops in air. If we had to do the equivalent problem in an aqueous medium, it's never something that even one would consider. So this is the modified picture, that now they are trying to squeeze it in. As they are trying to squeeze it in, instead of viewing this as a nice parabolic profile that was created by this continuum fluid, now you have these air molecules which are bouncing around. So if the gap was significantly larger than the mean free path, you have the typical continuum hydrodynamics that I mentioned. If the gap was extremely small compared to the mean free path, you have a Knudsen diffusion. And if the gap is comparable to the mean free path, which is the object of interest here, that's when you would have a non-continuum lubrication. So here I'm showing a lubrication force plotted against a function of gap width, where if you are somewhere far away, so as the gap width becomes, this is the gap width non-dimensionalized by the particle size. As you are in large gaps, once you go to large gaps, you have the continuum theory. And the continuum theory becomes this black dashed line, which is saying that the force diverges as the inversely with the separation, which gives us no contact in finite time. But as you get smaller, at a distance of order Knudsen, non-dimensionally, Knudsen here is defined as the mean free path divided by the particle size. So as it goes into separation of order Knudsen, the lubrication force is there, it's divergent, but it is a significantly weaker divergence. So that's all good. I mean, you have a weaker divergence, it's a mathematical answer and we could leave it there, but does it matter in the context of the collisional problems that we are doing? So it turns out, yes, because that detail of the weak divergence is what would be responsible for a finite time contact before you switch on any other physics. So when you are trying to make a calculation of collision rate, you shouldn't be doing the calculation purely with van der Waals. You need to account for the fact that a drop which is around 10 micron would have a Knudsen number around 10 to the power minus 2. So I'll show results in those regimes. So a Knudsen of 10 to the power minus 2 is going to influence what you have as the relative velocity of these drops, and that allows for a finite time contact without invoking anything else in the problem. So finally, now with all this, we are in a position to actually do these calculations. So you have two drops which are moving with respect to each other. There is an imposed background flow. You can have this background flow as a steady flow. You can have it as a turbulent flow. For the purpose of the calculation, the drops are small enough. The drops are sub-Kolmogorov. The collisional event are also happening in a sub-Kolmogorov regime because the Kolmogorov length scale is around a millimeter. So you would have the drops perceiving the background flow as a linear flow. So now you can solve for the relative separation. So R is the relative separation between the two drops. If you solve for the evolution of that relative separation, it has one part which is dictated by the flow. So gamma is the velocity gradient of the background flow. And the two spheres can be under the influence of forces F1 and F2. So if it is sedimentation, they will be different if they are different sizes. If it is electrostatics or van der Waals, they will be equal and opposite. So these parameters M and N, so that's what we have spent time calculating. So these are known as the mobility tensors in the parlance of low Reynolds number flow. But to just keep things short, I'll say that if there was no interaction, these objects would just be unity, which means they will just move like what Smoluchowski's calculation was, oblivious to the neighbor. They only realize there is a neighbor once they occupy the excluded volume. So you have a sphere 1 approaching sphere 2 under influence of flow or external forces, and the excluded volume is basically given by this transferent sphere 3. So if m and n were 1, it would just move not knowing that there was anything else, and the moment it breaches that transparent sphere 3, you call that as collision, which is the ghost collision. But now this m and n are functions of your separation, and with the non-continuum theory, they're also functions of the non-continuum parameter, which is Knudsen. So this is a typical calculation done for for illustrative purpose for a steady flow. So this is a uniaxial compressional flow. So the two spheres are present in a flow field where along this axis the flow is rushing in, and along the central plane it's basically rushing out. So the two spheres are also, the bigger sphere is approaching the smaller sphere. So you're looking at a combination of gravity and shear. And on the y-axis is the collisional efficiency. So it's the collision rate with interaction divided by the Smoluchowski-like collision. And the x-axis is a measure of how strong is settling with respect to shear. So if you go to the, if you're basically approaching towards the extreme on the x-axis, you're basically gone to pure settling scenario. Whereas if you are on this side at very small values of q, then you are in a regime which is dominated by shear or the flow. So you see there are these dependence here. And just to remind, there is nothing else in the problem. There is no van der Waals or anything else that is included in the problem. This is just an interaction done purely due to the non-continuum physics. So you have three different curves for three different values of Knudsen number. And Knudsen of 10 to the power minus 2 for a mean free path approximately of 100 nanometers translates to looking at particles of around 10 microns in size. So you can see that spanning this range, I mean, you are basically spanning a certain size gap that you have in mind. And as you change Knudsen, you start seeing that there is a significant change in the collisional efficiency that you have in this. So you have now a collision efficiency as a function of how strong is flow with respect to settling. And even these kinks that you see, these are not spurious kinks. They're artifacts of the fact that the paired topology, the trajectories actually become quite complicated when you have this slight change. But this is all very idealistic in a sense that the flow is a well-described background flow. So if the flow was not such a neat background flow, if it was a turbulence flow, and if we take typical values, and the typical values in the context of cumulus clouds, as I said, the turnover time scale would be around 4 × 10⁻² second. Your the eddy size would be around a millimeter. The dissipation rate is quite small. The Taylor-Reynolds number is quite large. And so we can now start comparing. The drops that we have in size in mind are significantly small when compared to the Kolmogorov length scale. At the scale of the particle, if you were to construct a Reynolds number, which is something which I said without a proof earlier, is very small. And you have now at least three time scales of interest here. The time scale tau p, which tells that how important is the inertia of the drop. So how quickly does it decelerate or accelerate. Tau eta, the Kolmogorov time scale. And tau nu is the time it takes for the drop to fall through an eddy. So using this, you can construct various non-dimensional numbers. And one being the Stokes number, which tells us how important is the inertia for these droplets. That is not negligible, but it's not really very large. Then you have a settling parameter, which is reasonably large. And you can use the two to come up with a parameter, the Froude number, that does not care about the particle dynamics. It's purely depends on the flow and gravity. So revisiting a very classical calculation in this, which is Safman and Turner's calculation of droplet collision. Safman and Turner's calculation was where you had two drops which were in the presence of a background flow. No gravity was involved. There was no interaction that was there. And if you make assumption that these were governed by Gaussian statistics for the velocity gradient, you can compute what would be the rate of collision. So if you revisit that same Safman-Turner calculation with two modifications, one basically being that you are allowing for gravity to be there in the problem. So they're settling. And the second one, which is probably more important, is that this is with hydrodynamic interactions in present. And hydrodynamic interactions which account for the fact that you can have these non-continuum interactions becoming very crucial when the gaps become small. And a third detail is that we also consider for the fact that the velocity gradient statistics here are non-Gaussian, unlike what was there in Safman and Turner's calculation. So I'll showcase the result immediately. So this is the collisional efficiency calculation. The green curve is what you saw earlier for the deterministic problem. There was like a prescribed flow that you had. The red curve is what you have now for the turbulence scenario. That you have a collisional efficiency, once again as a parameter, plotted against the relative strength of gravity to the background flow. Now, background flow is the turbulence flow that you have here. So that would be the Kolmogorov velocity scale. And you see that there is a significant dip that you start seeing because of turbulence as you start going to more settling dominated regimes. Comparisons, like I showed for the anisotropic particles, comparisons with experiments. It's hard to do exact comparisons of collisions of droplets at the scale of looking at pair interactions. There are very few experiments which have done those, but you can make indirect comparisons. So indirect comparisons as in you can have growth of droplets in a turbulent flow, in a homogeneous isotropic turbulent flow, and you observe the droplet size distribution as a function of time. And from the evolution of the droplet size distribution, you can try to infer what would have been the rate of collision or rate of growth which led to this. So basically plugging in a kinetic equation that gives us a DSD, and from that trying to back calculate this B is the rate of growth. So on the left panel, this is basically the rate of growth for different initial droplet size. This is, and on the left panel, this is around 88 second inverse is the shear rate in the turbulence. So the green circles that you see, these green circles are all from the theory. There are two kinds of green circles. One is filled and one is open. The filled ones are ideal with no interaction. The open ones are what you have with interaction, and the squares are what you have from the experiment where this indirect measurement was done. And here this is again shown for different values of Kolmogorov shear rate. The lowest Kolmogorov shear rate, which is around 25 second inverse, that is typically the shear rate that you would get in clouds. But the dissipation rate are quite high in these problems. These are more lab scale engineering turbulence in the context of sprays. So here, the ideal ones are not shown because they're usually much larger here. But the ones, the blue circles are the calculation from the theory / simulation compared with the blue crosses, which are the experimental data. So this is where we are at. And this plays a role because how precisely you use these collision rate determines how accurately you predict the DSD. This is a set of calculations done by Pinsky and Kane, where the growth of the droplet size distribution being done for different number density and different turbulence intensities. So the top left is basically the lowest turbulence intensity, whereas the bottom right has the highest turbulence intensity. And precisely what it does is the shape of the distribution, the number of large droplets that you get, those all crucially depends on the collisional kernel that you have. So there are different kernels which I've chosen here, pure gravitational, combination of gravitational and turbulence. And that serves as a motivation that it's probably important to actually focus a little bit on these collisional calculations. So with this, I'm just trying to close what kind of different physics we have been looking at. I focus primarily on the aspect of non-continuum. Just as a flavor, something that has gotten us excited recently is the aspect of charges. That if these drops were charged, what would be the consequence on the collision rate? Now here again, there is a significant departure from how people have been looking at charged colloids. Because there the suspending medium is an ionic solvent, whereas here it's air. So the interaction physics becomes fundamentally different. And the fundamental difference is that if you have like charge drops can have attractive interaction. So here in the size ratio being the y-axis and charge ratio being the x-axis, what you see in the light red are regions where the interaction in the near field, because far field is always repulsive. In the far field, they see each other as just monopoles. But in the near field, the induced dipole gives rise to attractive interactions. So this light red is the attractive interaction, whereas the dark red is when you have repulsive. So when you have let's imagine that you had the charge ratio fixed and you were scanning with size ratio. So as the size ratios were changing, you can have a significant attractive interaction, and it can also switch to being in a region being repulsive and then turning into attractive. So this is done for a dielectric constant of water 80. The yellow line is what you get for a conductor. So with this, if you now do the calculation for a drop that is 10 micron in size, and it has a charge of 200 fundamental units. So when you increase the size ratio and increase the charge ratio, so the black line that you see in the bottom is an previous calculation with continuum theory and van der Waals. Then when we include non-continuum theory, we get the red line. The pink one is with the combination of non-continuum and van der Waals. And then with the aspect of charge basically being there can be significant enhancements, especially when you are looking at pretty small charge ratios where the collision efficiency can become quite large. So with all that, I mean, it's probably something that can play a role. I mean, there is still a lot of caveats here that this is just the settling problem that we have looked at, how it plays around with turbulence and how it plays around with if there are other neutral particles present. I mean, those remain to be seen. So finally, to conclude, I mean, we have been looking at the microscale drop interactions in quite some detail, and then it eventually needs to be tied to the macro scale by going through this loop of how the droplet size will effectively grow. So thank you for your time, and I'll be happy to take any questions.
Thank you. Great. Questions?
Can you go back to the, you were summing the torques, right? And you had the balance of the three terms all summing to zero?
Yeah.
So is that for an instantaneous, like where's the turbulence in here, I guess?
So the turbulence is in the last term there. That's the turbulent drop. But this is instantaneous. There's an instantaneous balance in the problem purely because you were saying that at the scale of the crystal, the flow is predominantly viscous. So the lack of instantaneity would basically come about when you start going to larger size crystals.
So is S an instantaneous strain rate?
Instantaneous strain rate.
And then at some point, do you average over? If that's instantaneous, at some point you average, right? I guess that's the part that I missed.
So you compute what is your orientation at any instant, given whatever is your. So you are basically looking at the evolution of the orientation given whatever is the strain rate at that instant. So P dot is the rate of change of orientation that is dictated by the instantaneous velocity gradient and the strain rate. Once you have that, you achieve steady state and you do your ensemble averaging to find out what is your variance.
Over some distribution of strain rate and velocity gradient.
So you pick up your velocity gradient. So either you can pick it up from DNS, and people have done that. We did this. So we say that the velocity gradient is obeying this stochastic equation, and that gives us the velocity gradient, and we plug it in. But you could use it from DNS and do the same thing.
Right, okay. So you do it for a bunch of them and then you average over them given some distribution.
Exactly.
Okay, gotcha. Thank you.
Hi, just a quick question about the mixed or ice phase part. Have you considered the collision in that part? Collision between ice particles?
No, we haven't.
Okay.
So that's a tough thing to actually, because you have them in the sphere thing. We don't need to focus about orientation. I mean, it's just like the relative separation. But when you have the ice crystal, their relative orientation is also an additional parameter. So that's, I mean, the hope is to do that in a full numerical way. I don't think such simplified theory would work. You can do it numerically.
Okay, thank you.
I got a quick question. So you focused here on the collision part, but of course, once they make contact, they could bounce or do other things. And I'm wondering how some of these effects you talked about, like the non-continuum effect, could affect the bouncing of the drops once they actually collide, like if air gets trapped in there and stuff.
So if I'm not mistaken, like if it's around 50 to 60 microns and below, the reported values of coalescence or the coalescence efficiency is almost unity. So it basically dips once you go for larger drops. So whatever I'm saying here in terms of collision, that would basically cover the picture until it reaches maybe 45, 50 microns.
Okay, so there wouldn't be much of an overlap between those.
Yeah, so once it gets larger, you're absolutely right, the coalescence efficiency starts to dip, and then you can have bounce, you can have all kinds of fragmentation, all things can happen.
Yeah, that's kind of nice that they don't overlap then. They they're kind of separate regimes. Yeah. Okay, other questions? All right, let's thank the speaker once more.
Thank you.